we were to design a probe that will enter the solar system, and if we wanted to get close to planets so that we can send mini probes that will reach those planets, then this is the kind of trajectory that we will design.
July 1st, 2025. A new interstellar visitor streaks into the solar system, but within hours, NASA cameras detect a shock. Smaller objects are keeping perfect formation around the comet now called 3I/Atlas. Then Harvard steps forward, refusing to call this natural. They say the data points to alien technology, not cosmic debris. Why are leading scientists risking their reputations to declare these are probes, not rocks? And what happens if they're right? As Harvard sounds the alarm and NASA remains silent, we're left with the question no one can ignore. What is really orbiting 3I/Atlas, and why is it heading straight for us? Atlas, perched atop Cerro Pachon, began its nightly scan on July 1st, 2025. What started as a routine sweep for asteroids ended in a scramble. The first frames showed a single nucleus, a pale blur on a hyperbolic arc, nothing out of the ordinary for an interstellar comet. But as the telescope tracked the object through the Chilean dawn, something odd crept in at the edge of the images. Faint points, faint but persistent, moving in lockstep with the main body. Not streaks, not cosmic ray hits. These dots kept their distance, neither drifting apart nor tumbling closer. Within hours, the Zwicky Transient Facility in California joined the chase. Their wide-field cameras, tuned to catch supernovae and rogue asteroids, pulled in a fresh set of frames. The same configuration appeared, one bright core, and, on a handful of time-stamped exposures, tiny companions spaced like pearls on an invisible string. Each sequence, each new observatory, repeated the pattern. Gemini South, with its sharper optics, cut through the glare of the coma. The dots held their formation, fixed in relative position across the sky, even as the main object blazed onward at 58 kilometers per second. Technicians pored over raw FITS files, frame by frame, hunting for glitches. They checked for background stars, for satellite trails, for the telltale signature of detector noise. Nothing explained the symmetry. The spacing between the companions didn't change, not over minutes, not over hours. In natural breakups, fragments scatter, spiral, drift chaotically. Here, the separation was measured in arcseconds, unbroken by the comet's wild speed or the shifting stars behind it. The teams ran differential astrometry, plotting the motion of each dot against the nucleus. If these were random debris, their paths would diverge, pulled by gravity and the solar wind. Instead, every companion tracked a parallel course, as if bound by an unseen tether. The hyperbolic track of 3I/Atlas, steep, unbound, unmistakably interstellar, only deepened the puzzle. In the background, anonymous voices in control rooms traded clipped messages, double-checking timestamps, recalibrating optics, ruling out every artifact in the book. One thing was certain: whatever was keeping pace with the comet, it wasn't behaving like dust or ice or any natural fragment. The formation held, frame after frame, across 3 continents and 2 hemispheres. The anomaly was real. The debate over its nature would have to wait. Avi Loeb, chair of Harvard's astronomy department and head of Project Galileo, did not hesitate. Before the sun had set on the first day of discovery, Loeb's team convened an emergency briefing. The language was blunt. Given our ignorance about interstellar visitors, the hypothesis that we are seeing a technological signature should not be dismissed out of hand. Harvard's official statement hit the wires by midnight, calling for an urgent, coordinated investigation. The world's largest telescopes, Loeb insisted, must be turned toward 3I/Atlas, immediately before the window closed. Within hours, newsrooms from Boston to Berlin ran with the story. Harvard astronomers, possible alien probes orbiting comet, blared one headline. Loeb's previous battles over Oumuamua resurfaced, fueling both skepticism and fascination. Project Galileo's press office fielded a barrage of questions. Had they ruled out every natural explanation? Was Harvard really prepared to stake its reputation on the possibility of alien technology? NASA's response came the next morning. The official line, delivered in a tightly worded press release, was measured. All available data are consistent with a natural cometary origin. No evidence of artificial probes has been found. The statement was repeated, almost verbatim, in television interviews and social media posts. NASA's public affairs team emphasized the need for caution, reminding viewers that extraordinary claims demand extraordinary proof. The scientific community fractured along familiar lines. Some, like Neil deGrasse Tyson, chose their words carefully. Extraordinary claims require extraordinary evidence, he told a national news anchor. Let's see the raw data, the independent confirmations, before we rewrite the textbooks. Others, including outspoken theorists and space entrepreneurs, argued that dismissing the anomaly outright was itself unscientific. The controversy deepened as Project Galileo published a list of anomalies: fixed spacing, synchronized movement, a formation that defied the messy physics of cometary breakups. Loeb's team called for the release of all raw imaging, FITS files, calibration logs, tracking data, so independent astronomers could verify or refute the claim. NASA, for its part, promised transparency, but maintained that nothing in the images so far justified panic or speculation. The debate spilled onto social media, science podcasts, and even late-night talk shows. Was this the moment humanity had waited for, a signal from elsewhere, or just another case of wishful thinking dressed up as data? As the headlines multiplied, so did the sense of unease. What if Harvard was right? What if the world's best instruments had just recorded something no one could explain away? The stakes, for science and for society, had rarely felt higher. Precision, not chaos, defined the next round of observations. As the world's telescopes pivoted toward 3I/Atlas, the Hubble Space Telescope delivered its verdict. Companion points, if real, were not drifting, not spiraling outward as fragments do, but maintaining a constant separation from the nucleus. In each high-resolution frame, their spacing held, measured to within fractions of an arcsecond, a geometric regularity that defied the messy dynamics of cometary debris. The James Webb Space Telescope, operating in the infrared, confirmed the pattern. Over a 24-hour sequence, the same configuration persisted. No lag, no random walk, just a synchronized ballet around the main body. At NASA's Jet Propulsion Laboratory, astrometry teams fed this data into dynamical simulations. They modeled thousands of possible natural breakups, adjusting for solar tides, outgassing jets, and the subtle push of sunlight. In every scenario, fragments should have scattered. Instead, the observed points refused to obey, circling the primary with a periodicity so stable it rivaled the moons of Jupiter. The odds that random debris would mimic such choreography? Less than 1 in 10,000, according to JPL's Monte Carlo runs. For context, that's like tossing a handful of sand into a hurricane and finding the grains spell your name again and again across independent datasets. Charts from Hubble and Webb told the same story. The orbits traced by these companions were nearly circular, locked in a plane, each completing a revolution in just under 24 hours. No natural comet, not even in the wildest simulations, produces satellites with such perfect clockwork motion. The variance in their paths was so minimal that even seasoned orbital analysts hesitated. Was this a new class of gravitational resonance, or something else entirely? Something guided? The astrometry logs, stamped and time-synced, left little room for error. Each dot's position was plotted frame by frame, revealing a mechanical precision foreign to the physics of icy rubble. The JPL teams trained to distrust anomalies ran their tests again, then a third time. The answer did not change. Whatever circled 3I/Atlas was not drifting aimlessly. It was following a script, one written with cosmic precision bordering on intent. No official at NASA or ESA would comment on the record, but off-mic, a senior trajectory engineer confided, "If these orbits hold, we're not looking at a natural system, we're looking at control." The data was out there, open for all to see. The only thing missing was an explanation that fit the numbers. The first hint came not from the sky, but from the code. At the Harvard-Smithsonian Center, an AI algorithm, trained on years of comet-like curves, flagged something it had never seen before. Buried in the brightness data from Gemini South, a pulse repeated every 7 minutes. Not a flicker from passing clouds, not the random stutter of a tumbling rock. This was a heartbeat, steady, insistent, precise. The AI checked the raw frames, then the calibration logs, hunting for any sign of instrument error. But the signal persisted, frame after frame, night after night. A rhythm, a pulse, like a beacon in the dark. Spectroscopists at Gemini, led by a team with decades of experience dissecting comet tails, turned their attention to the color of the light. During the pulses, the emission lines sharpened and shifted. Nickel and cyanide, yes, but with an intensity that rose and fell in lockstep with the 7-minute cycle. A deeper scan revealed something stranger still. Every 12 hours, the entire coma flared green, as if a switch had been thrown. The flare wasn't a smooth rise, it was a spike, a sudden surge, then a slow decay. The pattern matched nothing in the catalogue of cometary outbursts. No natural process, no known chemistry produces such clockwork regularity. Michio Kaku, speaking on a late-night science broadcast, drew the analogy that caught fire across social media. If you saw a lighthouse blinking in the fog, would you call it a random wave? Or would you wonder who built it? He pointed to the Fourier analysis published by the Harvard team, showing the 7-minute spike and the 12-hour green flare as sharp peaks. No noise, no drift. Kaku compared it to the first detection of pulsars, when astronomers briefly thought they had found alien signals before settling on neutron stars. But this, he said, is no neutron star. This is something local, something moving through our system, and it's blinking at us. The speculation ran wild. Was this a communication signal, a navigation code for the companions, or the byproduct of a reactor cycling on and off? The Gemini team noted that the nickel lines, normally faint, buried in the glare, flared in perfect sync with the green surges. Nickel, a metal often used in high-temperature engineering, is rare in such abundance outside of artificial alloys. The 12-hour cycle, too crisp for random outgassing, hinted at a controlled energy source, perhaps driving the companions or powering instruments hidden in the coma. Skeptics pointed to the lack of peer-reviewed confirmation. NASA's Public Affairs Office issued a statement. No evidence of artificial activity has been found in the photometric or spectroscopic data. But the raw numbers were already circulating among astronomers, and the debate had shifted. The question was no longer whether the pulses were real. It was what, or who, was making them. As the world watched, the light from 3I/A TLAS kept blinking. 7 minutes, 12 hours, again and again, a metronome in the void. At Paranal Observatory, the VLT's FORS-2 instrument delivered a new kind of evidence, one that didn't rely on brightness or motion, but on the subtle alignment of light itself. Over a sequence of nights, astronomers measured the polarization of sunlight scattered off 3I/Atlas's coma. The results were stark. At a phase angle of just 7 degrees, the polarization dipped to -2.7%, a sharp, narrow minimum, unlike the broad, shallow curves seen in ordinary comets. By 17 degrees, the signal flipped, crossing zero in a snap inversion. Most comets show a gentle rise, a slow fade from negative to positive. Here, the curve was steeper, more abrupt, as if the grains were engineered for reflectivity, not chaos. The team compared these numbers against the Voyager database, drawn from decades of solar system flybys. No icy moon, no Centaur, no known comet matched the phase curve's depth or its razor-thin inversion angle. Metallic panel models tested in scattering simulations could mimic the steep dip, but always overshot the width and angle. The best fit came from grains coated in high albedo ice, mantled with dark organics, a recipe seen in the outer solar system, but never this extreme. Still, the data left a residue of doubt. The polarization was too deep, too narrow, too perfect for any random mix of dust and ice. In the control room, a polarimetry lead tapped the curve on the screen. If this were a Voyager flyby, he muttered, they'd call it artificial. The numbers didn't prove engineering, but they didn't close the door either. For the first time, the surface of 3I/Atlas offered a material clue, one that refused to settle quietly into the catalogue of natural things. In October 2017, astronomers at Haleakala spotted a visitor unlike any before. Oumuamua, the first confirmed interstellar object to enter our solar system, tumbled past the sun at a blistering 87 kilometers per second. It spun, elongated and silent, with no tail and no outgassing jets, yet its path defied gravity's script. As it receded, its acceleration ticked upward, a subtle push no comet theory could explain. Most experts pointed to invisible gas vents, but no trace of debris or vapor was ever found. Avi Loeb, then chair of Harvard's astronomy department, broke from consensus. He called for open consideration of artificial origin, igniting a debate that still burns in the halls of science. Now, 8 years later, the solar system braces for another close encounter. 3I/Atlas, discovered July 1st, 2025, is on final approach. Its perihelion, the closest point to the Sun, will arrive in late October 2025, just months away. The world's telescopes are poised for a front-row seat, hoping for answers before the window slams shut. For Loeb and his colleagues, the pattern is impossible to ignore. 2 interstellar objects in a single decade, both breaking the rules, both forcing astronomers to confront the unthinkable. If Oumuamua was the warning shot, 3I/Atlas is the test. The countdown has begun, and with it a new urgency to watch, record and prepare for whatever comes next. On July 1st, 2025, Atlas recorded the first confirmed images of 3I/Atlas, an interstellar object crossing our solar system at 58 kilometers per second. Multiple observatories verified its hyperbolic path and unusual green surges, while Harvard's Project Galileo called for urgent investigation into companion-like objects seen in formation. Evidence presented includes precise orbits, rhythmic light pulses, reactor-like flares, and polarization values unmatched by known comets. Yet, as of September 2025, no peer-reviewed study or officially released data confirms the existence or artificial nature of these companions. NASA continues to classify 3I/Atlas as a comet, while debate grows over its true identity. With perihelion approaching on October 29, 2025, the international scientific community faces crucial unanswered questions about origin and intent. What is clear? 3I/Atlas challenges our understanding of interstellar visitors, and its next approach will bring the world's attention back to the evidence. /Atlas's night side, showing no standard cometary signatures like CN or C2, orbital data from Caltech and JPL confirm repeated non-gravitational accelerations, and light curves reveal brightness surges every 3.7 hours, each aligning with trajectory changes. Ground-based and JWST imagery report an elongated, reflective shape, unlike any known comet, and document trailing objects spaced exactly 10 kilometers apart. Despite these findings, NASA's official statements continue to describe 3I/Atlas as a natural comet, and internal reviews remain classified as of June 2025. The true nature of the propulsion, the origin of its companion objects, and the source of its energy remain unresolved. What is verified? 3I/Atlas displays controlled movement and power signatures never before observed in an interstellar object. As it approaches perihelion on October 30th, 2025, the world's astronomers and the public await the next set of data, knowing the evidence so far has rewritten expectations for what travels between the stars. Agency continue to classify 3I/Atlas as a natural interstellar comet. Many findings remain under review, and some spectral data are still unreleased to the public. As October 2025 approaches, the date of its closest pass, researchers are preparing new campaigns to monitor any unexpected changes. For now, the scientific record shows a rare visitor with unexplained features and open questions, reminding us that not every mystery yields a simple answer. A path so precise that chance is less than 0.005%. For now, 3I/Atlas stands as the most anomalous visitor ever recorded, forcing science to confront data that defies every known category. Atlas has changed the discussion about what may travel between the stars.